When I was a student, I fell in love with the beauty of classical mechanics, Maxwell equations, and it happened that whenever an approximate expression showed up in relation with some specific case, I felt frustrated, as if physics has just lost its beauty right there. With time, I learned that uncertainty was part of our understanding of nature, and that every problem I solved had always some sort of uncertainty associated with it, and that an important part of the solution was estimating it. When I finally understood that, I began to like physics even more. Maybe I can make the same happen to you. They're teaching exercises where no calculation or expression derivations are involved, and this is one of them. The capacitance of two parallel plates is going to be approximately epsilon multiplied by S over L, where S is the area, L the distance separating them, and epsilon the permittivity of the medium between the plates. If the medium is also capable of conducting some current with a resistivity ρ, its resistance may be calculated using ρ multiplied by L over the area S. But if somehow we knew the capacitance, the resistance may also be calculated using the expression epsilon by ρ over C. No, deriving this expression is not what's going to be requested. That would be too easy. You replace C with the above expression, that. Now cancel the epsilons and take the L to the numerator, and we get the expression for the resistance. See? That was too easy. Here's your question. Would this expression underestimate or overestimate the resistance R? That's the question. First, you should ask yourself, why was the formula for the capacitance not an exact one? Well, because it was derived under this assumption. The charge corresponded only to the flux of the electric field within the plates, which neglected the stray field outside the plates. So the total Q is the one assumed plus the one from the stray field. When using the formula C equal epsilon S over L, we are ignoring the charge from the stray field. Being the real charge greater, then the capacity is underestimated in this expression. Stray field is not only smaller for the geometry, but also for the permeability of the medium being always higher than that of air or the epsilon zero of vacuum. That improves the approximation, but the capacitance from the expression being considered remains underestimated. Let's see the resistance now. The current density vector J between the plates is equal to the electric field vector E divided by the resistivity ρ. Outside the medium, the same expression will hold, only that ρ0 is huge in air and infinite in vacuum, so that the current density outside the plates is 0. That means that the expression for the resistance R equal to ρ L over S is accurate, for there's no current but within the plates. Since in this expression, the capacitance C will always be greater than the estimate used to derive it, we may conclude that the resistance will be underestimated when using that expression. Here's another exercise. Make an estimate with less than 30% uncertainty of the capacitance between the inner and outer conductors, considering that there's air in between. 30% uncertainty means that whatever the number you come up with must be somewhere between 0.7 and 1.3 of the real thing, right? It is being square what's new here, but if we made those conductors round, that would transform the system into the more familiar one of coaxial cylinders, right? The capacitance between two coaxial conducting cylinders is a textbook problem for exercising the Gauss law in that geometry. Here's a short reminder. There's a full one at the end of this video. But for now, the potential difference V was proven to be proportional to the total charge Q and to the natural logarithm of the outer to the inner radius quotient. So the capacitance Q over V resulted as this expression. But like that gruesome idiom goes, there's more than one way to skin a cat. And also there's more than one way to do this rounding. For instance, this one, inscribing both cylinders, it could be quite near the real thing, but you don't know how near, or even if it's greater or smaller. Same happens with this approach and with this one. You can't tell how near or if it's smaller or greater. However, in this case, the capacitance must be greater than the real thing, since the distance to every point is less or equal than in the case of the squares. And in this case, it must be smaller, for distances here are greater or equal. So we know that the capacitance we need to estimate is within these two extremes. Now let's hope that nature is kind enough for disallowing these values to go beyond the requested plus minus 30%. Let's put some numbers into the expression for the coaxial capacitance. Starting with a minimum capacitance case and calculating, we get 260 multiplied by 10 to minus 12 farads. Or saying it in the style of those who know what they're talking about, that's 260 picofarads. Now the maximum. Calculating. So the real thing must be somewhere between 260 and 385 picofarads. The geometric mean renders a number that's 22% from both the minimum and the maximum. So that's the correct answer to the problem. However, specialized tools exist that can solve these kind of problems to whatever accuracy is specified by using numerical methods. Just to mention a few, there is MATLAB, Fusion 360, Solid Edge, but there are many others that can solve partial differential equations with boundary value conditions. And here comes the cherry on the cake. Can we do better than that with what we know and without specialized tools? I think we do. There's a numerical method called relaxation. It is used by all the mentioned specialized tools for solving partial differential equations like the one at hand. But here, it will be implemented using just Microsoft Excel. The principle of this method is pretty straightforward. Let's start with the meaning of the Laplacian of V in x, y, z being equal to 0. That's it. In a cylindrical symmetry, nothing depends on z. All derivatives in z are equal to 0. So, calculus was about limits when the increments tended to 0. When going numeric, we need to come back from the limit to the finite deltas. Here's expressing the second derivative of v in x. That was the increment of the increment into delta x and into delta x again. Doing the same for y. But since both derivatives must sum 0, then we get, and hold this thought, stay with me, we're almost there. Okay, we were here. Now we isolate v in xy, and we get to the really important statement. The potential at any point is the average of the potentials of its four surrounding points. Next is making a grid of points spaced delta x and delta y, the size of which should be consistent with the required accuracy. In this case, say we use d equal 0.01 meter for both. Now let's prepare for Excel. We now need some initial values for the cells on that grid. First, let's take care of the boundaries. Since it is the capacitance, or in other words, the charge to voltage ratio, what's being requested, we can set any arbitrary voltage and then calculate the charge. That's when the potential distribution results from this relaxation method. Say we set the outer conductor to 0 and the inner one to 100 volts. The method consists in replacing the potential of any non-boundary cell with the average of its surrounding 4. Then do that over and over as many times as needed until it converges. Unthinkable without computers, right? The rest of the cells can be set to any number. For the iteration, we'll always bring it to the correct one, but bad guesses take longer. A good guess would be one between 0 and 100, say 50. Good. We are now ready for Excel. Open a new worksheet. Select now 25 columns and adjust their width to get a square cells. This way it will resemble the conductor system of the problem. Now identify the cells that correspond to the outer conductor. The cell content will be the potential at the center of the cell. Enter 0 volts at all boundary cells. Now enter 50 volts to all non-boundary cells. Select all the cells and center their content. This helps. Identify now the cells of the inner conductor. They're 4 centimeters from corner to corner. That is, from the center of K to the center of O. 5 cells, not just 4. Enter 100 volts to all the cells of the inner conductor. Let's verify. Good. Select all the cells and under conditional formatting, select color scales. It's a matter of taste here. I like this one better. Click now on the Developer tab. Oh, no Developer tab? No problem. Go under File, all the way to the bottom to Options. On the form that opens, select Customize Ribbon. On the right pane, check Developer, and you're good to go. Now click on Developer. Once there, click on Insert tab, and then on ActiveX Controls. Hit the bottom icon, top left. Draw a bottom anywhere you like, just big enough to hold the caption on. Right-click on it, and in the drop-down menu, click Properties. Change the back color to palette green, And now change the caption to on. Closed. This button is to start executing a piece of VBA code that implements the relaxation sequence. Here's the procedure. For each cell in the domain, calculate the average of the surrounding cells. Calculate its difference with the current value of the cell. Accumulate the absolute value of these differences in a variable called, say, error sum. Now replace the value of the cell with the average and go for the next cell. On every pass, update some sort of progress indicator, like for instance show the error sum. If error sum is still greater than the accuracy requirements, then repeat from the top. We are currently in design mode. Double-clicking on the bottom will open a Visual Basic form at the exact line where the code that implements the described procedure must be inserted. The VBA details are for you to figure out. The worksheet is available for download. You will find the URL in the description of the video. Now exit the design mode, click on the button and enjoy the show. We're done. Let's go for the capacity now. All we need is Q. Finally, we got the potential distribution. How do we get the Q now? We can calculate the Q in these conductors using the Gauss law. Let's see, the conductors were here. The more cells, the better, right? Say we calculate the charge in one of the sides of the outer conductor and multiply by 4. Now, we pick a Gauss surface, say, that one in red. Okay, we were here. The electrostatic field is 0, except for the area indicated by the yellow arrows. The Gauss law. And the fact that the electric field is the gradient of the potential. Going discrete now, the gradient component normal to the Gauss surface is the potential difference divided by the grid distance d. Also, the surface element is d multiplied by the length along the axis L. But wait, d's cancel. That simplified the expression further. The potential difference are the contents of those cells nearest to the conductor minus the potential of the conductor itself, which is 0. So this reduces to the sum of the content of the cells from 2 to 24. For the capacitance, just divide by the voltage and there we get the expression. Evaluating, we are now back to Excel once more. So the value obtained for the capacitance is wait, how good is this value? No uncertainty here? Answering this question will take even more work, for we must repeat the procedure but with a smaller cell. Using a cell 1/4 of the size renders 320 picofarads. This is 4.3% of the 334 picofarads we figured. Since this process must converge, repeating it with an even smaller cell cannot render capacitance beyond the 320 to 348 picofarads interval. So 334 is good within 5% uncertainty. For your peace of mind, I repeated the process with 1/4 of that cell and got 325. When calculating something in physics, in technology, in science, in life, estimating the uncertainty is as important as obtaining the value itself. When a value of a physical magnitude is given, it is just a point within an unknown interval. It's meaningless without its size. Is 325 picofarads, the value I calculated for your peace of mind, a better one than 334? It would be if we were not already neglecting the charge due to the stray field. This one could be calculated as 2.5%, approximately. So 334 picofarad with 5% uncertainty is about the best we can do. Here's the promised reminder of the capacitance between two coaxial cylinders. Let's start with the electrostatic field in a cylindrical geometry. Assume that there is a charge uniformly distributed in an infinite straight line at lambda coulombs per meter. Consider now a cylinder of length L with radius R, coaxial with the charged line. According to the Gauss law, the electric flux out of such surface multiplied by the permittivity equals the charge enclosed. For reasons of symmetry, the field E must be normal and constant over the generatrix surface of the cylinder, so the integral becomes the product of the area by the field E. The expression for the electric field intensity then is. Now the potentials in cylindrical geometries. In spherical geometries, there was this concept of potential of a point, which was the work of the electric field on a unit charge when moving it from that point to infinity. In cylindrical geometries like this, we are dealing with an infinite system, both in size and charge. This results in that the work for moving any finite charge from any point to infinity is infinity as well. Therefore, we can only deal with potential differences between points at finite distances from the axis. Okay, the potential difference between points 1 and 2 is the line integral of the electric field between these 2 points, and since only the radial component of the L can contribute to it, the line integral becomes just the integral of the electric field intensity between R1 and R2. Now, replacing the expression just obtained for the electric field on R, we get, but the R over R integrates as the natural logarithm of R. Let's evaluate at radius 1 and radius 2 for obtaining the expression. Putting it in terms of the total charge Q, and finally, isolating Q over V renders the expression for the capacitance between the coaxial cylinders of radius R and radius 2. And this is the end of the reminder. I hope it served its purpose, and until the next video. If you learned something with this video, maybe you want to subscribe to the channel. So long.